Okay everyone, today we're going to tackle a polynomial function and solve for all of its roots/zeros using the rational root theory. And after we're done, we're going to talk about multiplicity, how some answers show up more than once. The first thing I want to make sure I point out is what's known as the degree of the polynomial, the highest exponent. That's how many solutions we should have by the time we're done. So by the time we are finished, we should have a total of 5 solutions because the top exponent in this function is 5. Notice how it's in standard form. 5, 4, 3, 2, 1, 0. We don't have any missing terms. What we need to do is, considering that it's a long polynomial, is use rational root theorem, which means find all the roots of your last term. All the numbers that can divide 12 are 1, 2, 3, 4, 6, and 12. And divide it by all the numbers that are factors of your first term. I do not see a leading coefficient in front of x to the fifth, so I know that means a positive 1 x to the fifth. All of his factors come down here, which is good for us because there's only one of them. And when you divide each one of these, you have to consider that when you're doing rational root theorem, it could be the positive version or the negative version by the time you're done. Sometimes you see this symbol, positive and negative. So 1 divided by 1 is 1. That could be positive or negative 1. 2 divided by 1 is 2. Could be positive or negative 2. 3, 4, 6, and 12, as we can see. And what I have to do is just start with 1, any one of them, to begin. And I have to do synthetic division to try to start breaking it down, hopefully to the point where I can start to factor it. So positive, negative 1, positive or negative 2, 3, 4, so on and so forth. We're going to have a total of 1, 2, 3, 4, 5, 6, but because it's positive or negative, a total of 12 possible roots here. So we're just going to start with positive 1, see if it works. I bring down positive 1, and I put it in a box. And then I write down all the coefficients of the polynomial. That would be 1, 1, negative 9, negative 5, positive 16, positive 12. I draw a line, and I start to bring down numbers with first 1. And I take my box number and I multiply the number I just brought down and put the new answer in the next slot. So 1 times 1 is 1. I now add these two together. 1 and 1 make 2. 1 times 2 is 2. Negative 9 plus 2 is negative 7. 1 times negative 7 is negative 7. Combine these two, I get negative 12. Negative 12 in the next spot after I multiply by 1. 16 plus negative 12 is a 4. 1 times 4 is 4. And 12 plus 4 makes 16. That I cannot have. What you're looking to get in this last spot is a remainder of 0. If it has a remainder, it is not a solution or root or 0, whatever you want to call it. So I'm going to move on to the next one. I tried positive 1. Now I'm going to do negative 1 through the same process. Drop the 1. Negative 1 times 1 is negative 1. 1 plus negative 1 makes 0. This makes 0. That makes negative 9. That makes positive 9. This makes 4. Negative 4. And negative 1 times positive 12 is negative 12. There it is, the remainder of 0. As soon as I get that, I know that this number works. This is a solution. It'll be one of the answers I put down. One of the 5 answers I know I'll have by the time I'm done. And what I do now is create a new polynomial off of the remainders that we got down here. So going back to my beginning root, when I make my new polynomial, that has to drop 1. So from x to the fifth, it's going to go down to x to the fourth. And it looks like I have 1x to the fourth plus 0x to the third minus 9x squared plus 4x plus 12. It's still a rather long polynomial. So again, I'm going to take the roots of 12, the roots of 1, luckily I already have them up here, and I'm going to try some more of them. Since negative 1 worked last time, I'm going to try it again just to see if it happens to show up a second time. Coefficients are 1, 0, negative 9, positive 4, positive 12. Draw the line and bring down 1. Negative 1 times 1 is negative 1. Add these guys, you get negative 1. Negative 1 times negative 1 is positive 1. Then we get negative 8. Positive 8, we get 12. and negative 12 gives us a remainder of 0, which is exactly what I want. So negative 1 has showed up twice. It showed up here and here, which means it has what we call multiplicity. In fact, it has a multiplicity of 2 so far, maybe even more by the time we're done. What we need to do now is take our remaining numbers and make a new polynomial. We started with x to the 4th. Well, technically we started with x to the 5th, but then the 4th. And now we're going to have 1x to the 3rd power minus x to the 2nd power minus 8x plus 12. Because it's a 4-term polynomial now, I'd like to factor by grouping. If I could cut it in half and factor out a GCF here and here and get the same binomial twice, that would be fantastic. But I can already see that's not going to happen. I'll pull out x squared and I'll get x minus 1 on the left. Over here I can pull out, perhaps a negative or a positive 4, but that's going to give me 2x plus 3 or negative 2x plus 3, whatever I pull out. So I got to keep going back to rational root theorem. For the sake of time, I'm going to tell you that I already know something else that works. It is the number 2. So I'm going to use 2 in the box this time. My coefficients, 1, negative 8, 12. Draw the line. Drop my 1. 2 times 1 is 2. Negative 1 plus 2 is 1. 2 times 1 is 2. Negative 8 plus 2 is negative 6. And 2 times negative 6 makes negative 12, a remainder of 0. Now I have a third answer. Positive 2 also works. Now I just need to write down my new polynomial with just 3 terms. I'm going to drop from x to the 3rd now to x to the 2nd power plus x minus 6. 1, 1, and negative 6. This, I notice, basic trinomial from Algebra 1 can be factored. I'm looking for 2 numbers that multiply to make 6 and subtract to make 1, which is what's in the middle. That would be 2 and 3. So now I got my x, 2, and 3. I know with the back sign being negative, the 2 answer signs have to be different. The bigger one will get whatever's in the middle, so I get a plus 3 and a minus 2. Now I just need to take each one of these guys, put them equal to 0, and solve. Again, once you get good at this, you don't have to keep writing this step out. This one-step equation. We know it's going to be positive 2 and negative 3. So I notice again there's positive 2, which we already put a check mark by, right? So here's our other answers. Oops, didn't put a very good equal sign there. Negative 3. So I end up with negative 1, 2, 2 again, and then negative 3. So what I have is some multiplicity. The number negative 1 shows up 2 times. So I can say negative 1 with a multiplicity of 2. 2 does the same thing. It shows up twice. Positive 2 with a multiplicity of 2. And then the number negative 3 showed up only once. So this one has a multiplicity of 1. Hope that was helpful. Have a good day.